I'm going to talk to you about our toilet system based on a process called hydrothermal carbonization. Before I go on, already started going on, just like to say thank you to the Melinda Gates Foundation for their support of this project, and a big thank you to the organisers of this conference for letting me come and talk about it to you today. So, just tell you a little bit about the team at Loughborough. There's 4 other academics involved in this project. It's led by Sir Hale Khan from the WEDEC Centre. There's Richard Holditch from Chemical Engineering, Andrew Wheatley, Civil Engineer, and Diane Guy, School of Design at Loughborough. And then, so they're the academics involved in this project, but the person who's done a lot of the work that I'll talk about today, PhD student Eric Danso-Botang. He even gets his picture on the slide because he's done so much effort and he looks so much better than the rest of us, especially when he's got his cool shades on. So you can see him putting together the display that we took to the Seattle Fair there. So this is a brief outline of what I'm going to talk about today. So quickly remind you what the Reinvent the Toilet Challenge is about, and then talk about the main part of our process, the hydrothermal carbonization, talk about what it is, and then tell you about the work we've done on understanding the process and establishing that it can be used for our toilet system, and then talk about the way we're going to implement it for our system, the continuous flow system, and then talk about the coatings we intend to use as a way of minimising the amount of flush volume used in the system, and then finish with a short piece about the design principles we're applying to this process. So, the RTTC, Reinvent the Toilet Challenge, these are the key points as we saw them when the challenge came in. There's a lot more to the challenge. If you don't know about what this challenge call was, do go to the Bill and Melinda Gates Foundation website and have a look at it. There's a lot to it. But I think in essence it can be, a lot of it can be reduced to these points here. So it was a call to develop a new technology for handling and processing human waste and turn it into useful products. In fact, handling is probably the wrong word to have used now I come to say it out loud. We want to get away from handling human waste. One needs to do all this for about 5 cents per user per day, even less if possible. Ideally, the process needs to work within 24 hours. So cover get rid of all the material to save products within 24 hours. It needs to work off-grid. That's something we've really worked hard on. And just as important as all those sort of technical points, it needs to make the toilet experience for the user of the toilet as pleasant and safe as possible. We've heard through the conference, various talks, how people do feel unsafe using toilets in terms of the sanitation issues about smell, disease, and factors like that. There's also factors about some areas are not safe and people do not want to be walking out at night to somewhere where they feel very nervous. So we need to take all these things into account. So the RTTC challenge went out to various groups around the world, and it landed on Sir Hale's desk at Loughborough, and he immediately realised that it was an interesting project, but that within the WEDEC Centre there wasn't the expertise needed just within his department. So one thing that Loughborough's established over the last few years is a system of bringing together expertise from around the university. Now, most universities in the world have great knowledge in various areas, but most of us are not very good at talking to each other and sort of sharing our experiences and our knowledge. And Loughborough's realised this and put together a scheme for bringing together knowledge where possible through what we term interdisciplinary research schools. So that, and through this system, a team was put together. I told you about the members of it. We got together to see if we could put together a useful bid for this challenge. And this slide is about how we saw how the challenge could be met with what we are able to do. So the approach we took to the problem was that a fundamental one at the very beginning was that liquid-solid separation is going to be difficult. We realise there are these urine diverting toilet systems and things, but they don't always work. You know, things go wrong, you get outbreaks of diarrhea, people just rush in, things go wrong, people vomit down toilets, the wrong things get thrown down toilets. So we wanted to make sure our system worked in as robust way as possible, so stuff just goes in and we process it. So that was a decision we made early on, and that really drove the direction of the solution that we've got to. So we wanted to, with that, we wanted a system that works with liquids and with solids. The next design decision following on from that is that the timescale of the challenge means that the anaerobic digestion processes are realistically are too slow for this challenge, and that's coupled with the fact that anaerobic digesters are not easy to install in many locations, particularly where developments have occurred. You need a lot of space to dig holes, bury these things. And at the end of the day, there's still effluent that needs to be dealt with from these digesters, so they don't solve the challenge problem. One thing that came to mind is a process called hydrothermal carbonization, which is gaining interest in Europe in particular as a way of dealing with biomass in general. And we knew about that, so we've seen it worked for vegetation, so green waste that gets put in the municipal waste stream. So the question was, can it work with sewage type material, and can it be made to work on the scales of numbers that would apply for this challenge? So, what is hydrothermal carbonisation? Well, it's essentially, in fancy chemical terms, it's the dehydration of carbohydrates. So, we show the simplest version of the process here. Essentially start off with a simple sugar molecule there, and strip out water from it, extract water from it. And it's a process that works. You take organic material in presence of water and you heat it under pressure to temperatures in the range of 140 Celsius to as high as you can go depending on the pressure that you have. And under those conditions, this chemistry happens as if by magic. Essentially, what happens is you strip out oxygen and hydrogen from the carbohydrates in the material that you have, and you get left with a very close approximation to coal. And in fact, this chemistry is essentially what the chemistry that goes on underground when fossil fuels are made. This is how coal comes to be under the ground. But it turns out that you can do it essentially in a pressure cooker above ground, and rather than on the sort of geological timescales, it can happen in a few minutes to a few hours. So we get the high carbon fuel-like material, so with the carbohydrates, with the water stripped out of it, and you'll notice in the equation there's energy left over as a byproduct as well. It's a strongly exothermal reaction, so once this reaction starts going, it gives out energy, quite a lot there, so you can see down the bottom, about a megajoule per mole of energy is given out from this process. It's we don't just have carbohydrates in most biomass, and particularly within food. There's lots of other stuff, but essentially the chemistry works the same. The water is stripped out. You also get nitrogen stripped out of the materials as well. And at the end of the product, we get a range within the mixture. You get a range of various soluble and volatile organic materials. Depending on the pressure you're at, you get various gases produced as well. But the main product is essentially a coal-like material that is very easy to separate out. So it's a water-based process, and it's an exothermic process. So once we decided that this was a possible route to use for our process, we wanted to make sure that we understood it and make sure that we could move our research in the right direction. So we did a lot of work on understanding how the process works, what the energy inputs are, and how long we have to process the material for until we can filter out the material. So and this is the work that Eric did. So we did a lot of measurements on simulated fecal matter and also on primary sludge from the local sewage works in Loughborough. So we took sludge that was straight from the collection point at the sewage works, so it's approximately an hour old, from the inlet pipe at the work. So, and it was then refrigerated and stored until we did these measurements. So it's reasonably fresh sludge, but it will have other materials in with it, backwater and things like that. So we did a set of batch-based measurements. We looked at a variety of different loadings, so 5% solid loadings, up to 25% loadings by weight. Range of temperatures, 140 to 200 degrees Celsius, and a range of conversion times, so from 0 to 6 hours approximately. And we had a look at what came out. So, and this is the sort of thing we got. These are images of the simulated material. And this is what happens at 140 degrees here. So starting at the top left there's a sample that's been in for 20 minutes or so, and essentially it's unchanged from the 0 time. And going through to about 6 hours on the bottom right image there, hopefully you can see, even at the back there, it's started to darken up, the changes have occurred. But as you see from the notes there, very little, if any, true carbonization has occurred within the process at these timescales. Moving through the temperature range, 160 degrees now, you start to see there's much marked change in the colour, and at around by 6 hours or so there's a good degree of carbonisation in the process. You can see that the last two of the samples there, they're really getting quite black looking, so there's good degree of carbonisation, and we find that with these samples, when we take it out, the solids are very easily filterable from the remaining liquid. To 180 degrees, really the process is getting much quicker now. We don't need to go anywhere near the 6 hours to get to full carbonisation. And within 30 minutes or so, you can tell that the process has begun. And 200 degrees, it's hard to stop the process happening. So you see there, within 40 minutes or so, it's really gone pretty much to completion. So we can see that the process works, and we can see that we have control over the time scale over which it works there. So we've got that. We know the process works, but we've done quite a lot of detailed analysis of the rate at which the process works, and in particular, we've looked at the rates at which the chemistry occurs. And the main way we've done that is through studies of the ratios of the carbonised mass at the end to the input mass at the beginning, and using really quite a straightforward Arrhenius analysis, looking at these ratios, we can work out the activation energies of the process, and we can also get the rate constants for it. Show the data plotted there. The red dots on the graph, that's for the reaction for the synthetic material. The blue diamonds are the way the primary sludge behaves. From the slopes, you can see that the slopes are really pretty similar, so the reaction rates are similar. We see a different activation energy for the material, so it's actually easier to get the process going within the sludge-like material than it is for the simulated material. But they're not too far apart, so we think that, well, we're confident the same chemistry is happening there, and they're happening at reasonable rates. We've done a lot of other analyses on this data. In fact, it goes on forever. Poor old Eric. He's just graphs coming out of his ears. I won't inflict those on you, but just to sort of summarise what we got from this analysis is that the hydrothermal carbonisation process does work very well on both the synthetic material and the primary sludge. We do know that we have studied the carbon hydrogen oxygen ratios, and we're confident it's this dehydration process that's dominating the chemistry that's going on. And really the key point as far as the challenge is concerned is that we found that we have an absolutely sterile material that's very readily filterable after only 15 minutes at 200 degrees. So that's a really important point for us. We get, after just 15 minutes, we're at a stage where we can filter off and start using the material. We don't need to go to full conversion with that process. What we're interested in doing is converting this material into something we can handle and something we can use. If we went on any further, we'd just be throwing energy away, but really we want to conserve energy within this process. So at 15 minutes, we've got something that we need, so that's good. Right, so the bottom line of it is, although we can work within 15 minutes, because we've got all that water there, that there's an energy penalty associated with that. So it takes a lot of energy to heat water up, about 4 times as much energy to heat a kilogram of water as to heat a kilogram of the organic matter. So there's a big energy cost there. And there's a question mark over whether there's enough energy in the system to drive this process and make it self-sustaining so we can stay off-grid. We've done the analysis, and it turns out that yes, there is enough energy there. It matters what the solid to liquid ratio is, but at 200 degrees, with a decent amount of energy in the dry solid, so 17 millimeters per kilogram is a value that's been mentioned in talks this week. So using that, at 5% solids, we do get energy break-even, so the process will be self-sustaining. Even at very low energy values, if we can get to 16% solids, then the process will work. So we can do it, but we have to be careful how much flush water is used. I'll be given the hurry up, so I'll skip. Initially, we had a batch-based process in mind, but we've decided to move to a continuous flow system. So we have a process that moves the material through a continuous flow reactor, so that, which has a great advantage is that there's no heating and cooling. We keep everything at the same temperature. The output liquid and steam that comes from the system is used to heat the material before it comes in, so it cycles round and conserves heat. We can extract from it the volatile gases and use them as a fuel for the heating, and we can also extract the biochar using a simple filtering system. So we can do this, there is enough energy there, and we can separate stuff easily. The filtering system, very briefly, what we intend to use is the sort of slot filter you see there on the right-hand side. It turns out that we tend to think of filters being sort of round holes that stuff is forced through. If you actually sort of study the way things work, a slot filter like that is much better for filtering material. We get much better transfer of liquid from one side to the other, and they do not clog anywhere near as easily as the round filter, so we'll be using a system like that. So the other thing that's caused some interest in this project is the coatings we'll be using to minimise the flush volume. What we want to do is stop. We don't want skid marks on the bowl so that people start flushing water through and diluting our systems. We want to avoid that. People do use hydrophobic coatings for these sorts of applications, but there are problems. You probably won't be able to see it at the back there. This is a photo of a toilet from a train that uses a standard non-stick coating to try and stop stuff sticking to it. Hopefully some of you at the front can see that in the middle the coating has been eroded away, and actually the steel bowl is starting to rust away, and the droplets of water on there, although it's essentially a Teflon coating, it's not working that well. The water is staying there and it's semi-wetting the surface, so these coatings are a problem. Yeah. So what we've moved to, what we've used is a system that uses a hydrophilic coating on the surface of the bowl. It can be processed from a dilute water solution, so it's easy to handle. And what it does is it leaves a wetting layer on the surface. Rather than an anti-wetting layer, water gets onto the surface, gets underneath any contaminants there, and washes stuff away. So these show the action. The successful one. If you look at the middle row here, this coating here, we go from a brown sticky stuff as our simulant material on glass slides, and then we wash it off using typical flush rates. And you can see here that the hydrophilic coating leads to very clean surfaces afterwards. This is for example, down the bottom is a non-coated material. So these coatings, they very well flush material out of the system. We've also got a big effort into the design of the interface. Unfortunately, I've got to move on from that. But we will be launching a national design competition, getting students around the UK involved in our interface for that project. So let's just go to the conclusions now. The hydrothermal carbonization process is viable to process human waste, and can be self-sufficient. So it does meet the Reinvent the Toilet Challenge criteria. We do need to work on that water-solid ratio, and we're going to use responsive layers to help us with that. Okay.